these sort of beam models. And you can select whatever resolution you want. So, I mean, typically the lowest resolution you would want to use for origami would be around 6 base pairs, and the highest resolution would be 1 base pair per backbone. So one thing you'll notice during these simulations is that the structures in the coarser side of things relax very quickly. That's because there are two reasons for that. One is that the coarse models they have just naturally faster kinetics because the beads aren't coupled to each other as tightly. So they're every time you step one direction, you're not being forced to step back by your neighbors. The other reason is that the time steps that we're able to take with these coarse models are larger. You run into problems with numerical stability if you take large time steps with a high resolution model. Yeah. So I'll talk now about the potentials in these polymer models. So first, the intrahelical potentials. So the first thing that we have is a bond between every pair of backbone beams, which are shown in blue. So we get the strength, we get the rest length of the bond by knowing that there are 3.4 angstroms for every base pair. The spring constant for the bond is obtained from experimental measurements from stretching double-stranded DNA in an optical trap like this. An experiment like this will produce data that looks like this, where you have extension of the DNA duplex on the x-axis and force on the y-axis. And there are a number of regimes, and the DNA I'd like to highlight is this green curve here. So the regime that we would be interested in matching for the strength constant will be when the DNA is pretty well stretched, but not stretched so strongly that it's melting. If you put a large force on the DNA, the strands will actually separate. And we don't really want to build that phenomenon into our beam model. So the regime where it's stretched but not melting is right before this plateau in this little region C. So if you just fiddle in your line to the curve there, you get a spring constant of about 1,000 piconewtons. An elastic constant of about 1,000 piconewtons. So similarly, for the angle potential, we want to match something that's known about the polymer properties of the DNA. The natural quantity to look at is the persistence length. And actually, does everybody know what the persistence length is? Please raise your hand if you know. Okay. Raise your hand if you don't. No, I'm sorry. So most of you know what persistence length is. Briefly, it's the length scale that if you travel along the DNA, it's the length scale at which you start to lose the correlation of the direction. So a polymer is sort of a wavy object, and if you go far enough, you won't be pointing in the same direction that you started. So mathematically, that gets expressed with this equation. So the average value of the cosine of the angle between tangents will decay as 1 over the exponent of u minus contour length over persistence length. And if you have an average quantity like this, you can write out an integral that expresses the likelihood you can express this average through a configurational integral. So the numerator has this cosine theta in it, and then it's Boltzmann weight and something that just says, well, okay, the theta that we measure based on integrating over all possible coordinates is the same theta that we're interested here. And then in the numerator, you just integrate over all possible states ultimately. This can be pretty easily turned into an expression at the right. And if you're really good at integration, maybe you can come up with a solution to this. I could not, so I took the easy thing. I did the easy thing, which was to numerically solve the right hand of the equation, the right hand solution with the left hand, so that in the regime that we're interested in, these contour lengths, this exponential term is roughly, it almost looks linear. So what you can do, so these two plots share a y-axis. So what you can do is, say you have 3 base pairs here, you can look at the contour length, trace your way up, see where you are on the y-axis, go over to the next plot, and trace your way down, get a spring constant. So that's actually what we do in our code. Okay, so for the dihedral angle potential, we have a similar quantity, which is the twist persistence length. So this is the distance along which it will travel along the DNA that the twist, or essentially the orientation about the azimuthal angle of the DNA, or about the DNA axis, becomes along forward. So that there are actually a number of experimental measures for that, but we've chosen 90 nanometers, which seems to be working pretty well. And again, you can write down an integral for this and solve it. This one actually can be done analytically. I didn't write down the solution. It's nasty. Yeah. But so this is how we get our dihedral angle potential. I didn't introduce these green beads. These are orientation beads. They don't interact directly with anything except for their parent beads and with each other through a dihedral angle potential. So that's sort of like a twist across or about this bond. Okay, so then that summarizes all of the bonded interactions in the model. We also have non-bonded interactions. So if two DNA strands approach each other, or two DNA helices approach each other, they should feel some repulsion because they're highly electrostatic or electronegatively charged. So rather than assume the bicubical formula or Boltzmann kind of approach for electrostatics, we actually ran simulations of DNA duplexes and measured essentially the mean force as a function of the distance between those duplexes. So these are small simulations, and they weren't too bad. We only did this at one concentration, iron concentration. So currently that's fixed in our model. And then to get the pair interaction, we basically do a sum over the interactions between multiple beads that would be composed in that same system. So basically build the system out of our coarse-grained model. Look at the interaction. Look at the different interactions, and we optimize the parametrically defined potential. Okay, so then to construct DNA origami, you have to have crossovers. So we model those with the bond, harmonic bond, that's derived to match our the distribution of distances between the bases involved in crossovers that we've seen from our all-axis simulations. And in addition to that bond, crossovers, at least in origami, tend to be aligned. We found that was necessary in order to get decent looking structures to add some angle and dihedral potentials that keep the bond here, the crossover bond, orthogonal to the direction of the DNA helix on each side. And we also found that it was necessary to keep these DNA nuclexes roughly parallel to that dihedral potential that moves from this bond to this bond. And these potentials haven't been optimized yet, but that's something that we're planning. So then the last thing is that some of our models don't have these orientation beads, and in that case, we try to capture the twist of or the twist stiffness of the DNA by having a dihedral angle potential between crossovers. So this is there's the solution to that integral. This is this basically captures the twisting structure when you don't have a local representation. So it's only for the coarsest model that we use. Okay, so so when you start typically with say a CAD nanostructure, and then we have code that will place a bunch of beads at the ends of each duplex and at all of the crossover sites. And then these get placed in between at a sort of user-specified density. And then we add intrahelical bonds. We add our crossover bonds. And, oops, sorry. And we have also our crossover angle and dihedral terms that get added. So that's sort of a quick summary of how we actually go from CAD Nano to our coarse grain model. Okay. And then once we've run a simulation, the structure relaxes, and we want to return back to, so we have a bead-based model that we run a simulation of, and then we want to return to sort of a parametric description of the DNA nanostructure. So what we do in essence is we fit a spline, a three-dimensional spline though, as opposed to this 1D example, through the coordinates of each helical stretch of DNA. And in addition, we use a quaternion representation of the orientation, which, if you're unfamiliar with this, it's sort of like a vector that represents the orientation of the object. And the nice thing about quaternions is that you can interpolate between them in a really natural way, which you can't do with rotation matrices. So that's sort of how we're able to map between different resolutions. And this system is already available in a web server that we have. So you can upload your JSON file, and our server will run these coarse grain simulations and return an atomic structure to you. And it runs them on our own machines. So you're welcome to use that. But so for example, I'll skip that. So okay. So we've applied this now to a number of systems, and these are sorry, I forgot what I was going to say here. So these are examples of structures that you could easily simulate on our web server. So this pointer structure, you could pass through a web server. An hour later, you get a result like this. Similarly, you could simulate these twisted structures from this paper from William Shee's group several years ago, and you get nice results very quickly. would have some decent agreement with the images from that paper. But if you want to do something a little bit larger or more complex, something that starts out further from its initial condition, you'll have to actually run the simulations on your own. And for that, we've provided two methods. The first is to use a simple command line script. So we call it mRDNA for multi-resolution DNA simulations. And then you just provide your the simplest usage is to provide just the structure file, the design file to the script, and then it'll run this cascade of simulations. And you can give it options to make the simulations longer or shorter, depending how you like. And this is covered in our tutorial today. But we also allow you to do this from a script. So it's not a difficult thing to use, and this is also covered in our tutorial. For now, I'll focus on some possible applications of this command line utility. So these structures with programmed ends are two. They're all initially straight, and I mean the 0-degree one, yes, we definitely simulate on our web server. But for the rest of them, it will take too long to actually get a converged result. But here with the mRDNA scripts, we're able to easily run these simulations and confirm that we get some reasonable looking result. So in the tutorial today, we have a sort of miniature example of this. We've made it really small so that it's easy to run on an Amazon workstation. You'll get a result in like 3 minutes or something. So another application of the mRDNA script is that you could look at all of these moving nanostructures, for example, from the past. So one of the first things that we were looking at was this slider object, which Sartak was simulating when he did a rotation in our group, so a new graduate student. And it worked reasonably well. We don't get perfect agreement with the experiment, but it's not too bad, considering that we haven't tried to match the ion conditions or anything like that. And we have an example in our tutorial where you'll actually run this simulation, although a very, very short version of it. And then you can measure the extension yourself and sort of recreate that little project. Other structures, we've also simulated some of these other kinetic structures from the Castro group, including this crank slider, which has both a hinge and sliding speed, and these Bennett linkages, which are designed to fold, to reconfigure in a sort of complex way. And for the latter, we've actually been able to look at some comparisons with recent experimental data coming from Castro's lab. There was a paper where they were able to obtain three-dimensional single particle Crowdian reconstructions of these objects, and they were able to measure from that the dihedral angles, or the angles between the planes in the structure. Briefly, the distributions that they obtained for alpha, which was the angle between the plane formed by these two arms and these two arms, and beta, which is actually I'm a little unclear on beta. In any case, we did this analysis, and we were happy to get pretty similar distributions. Yeah, sorry, this analysis is a little okay. Another application that you could do with the script is just to take a structure like this box from Victoria Berkedal's group and run a simulation of it folding, and then map to high resolution, and then look at specific sites on the box that are labeled with red dyes so that you can try to compare to their fret measurements. So we did this recently, and it's not yet published, so I'll just show our distributions and say that, yeah, I mean, it's like a semi-quantitative comparison, but basically things appear pretty well. So I think the moral of this story is that a tool like this can be useful if you're thinking about tagging your structure with red dyes. It's a good idea. I mean, you might as well run a quick simulation and check if those labeling sites are good, because it's almost free. It takes half an hour, an hour, or something like that, and you can just see how far my proposed labeling sites are. Am I going to get a good thread efficiency, or am I not? And so again, in our tutorial, we have an example with a smaller box from Computational's lab, which you can simulate with just a command line argument like this, or just a command like this. Yes. So then the last example that we have is this circular DNA structure from Young's group, which when you run through the mRDNA script, looks like it folds nicely. But if you turn this thing, well, it's not that nice. So to tackle something like this, actually, it's necessary to move to the scripting methods. So for the rest of the talk, that's what I'll focus on. It's not too difficult to take half the structure and bend it 90 degrees. It's actually hidden right now behind this axis. And then you can quickly and easily fold the structure and obtain an atomic model. Takes a little time. Yes. So the way that's done is, I mean, we have tutorial materials that show you how to do similar things. We don't have that exact example, but you can. No. Sorry. Yeah. So we have switch laser pointers. Don't do that by accident again. So we have some simple commands. You start with a model that the tutorial introduces to you. You can get a rotation matrix very easily, and then you can just say, okay, rotate my model and rotate it about this position. So it's very easy to do, and similarly, if you want, you can translate or rotate just a piece of the model, a single helical segment, and those approaches are covered in our tutorial in the sort of last part of it, in an interactive Jupyter notebook, which is kind of fun. Okay, so then the last thing that I'll talk about is sort of it's the project that this material is taken from, which is featured in our tutorial, and it's a study that we recently published with Ulrich Kaiser about a DNA nanostructure that's designed to be captured in a small capillary, and then it's labeled with two thread pairs. Well, with one of two thread pairs, in order to probe the elastic deformation of the object in response to an applied bias. So that way you can apply potential, and then with a optically read out what that potential is. So the dream is then to take this object, put it on neuron. I don't think Kaiser's there yet, but that's sort of the motivation for that for creating this proof of concept structure. So the Kaiser group developed a model of the nanopipette using COMSOL, which is a popular continuum finite element package, and we were able to take the results from this finite element package, which incorporates information about the applied bias, but also what your ion concentration is, and the ability of ions in the system, and charge on the glass nanocapillary, these things, and it provides you with a potential, and then we can create a three-dimensional potential out of that. And the simulation engine that we have supports using 3D potentials to apply forces to these sort of E-based polymer models. So the construction of this 3D potential isn't covered in our tutorial, but using any 3D potential that you get, whatever software package, is. But briefly. And in this project, we also cover some sort of subtleties of modeling. So this is a view of the CAD nano design of that structure, which I back up actually. You can see there's this long double-stranded DNA, which is used to actually capture the object. So it's about 800 base pairs, and it's modeled in CAD nano with, with an insertion. If you look behind all these crossovers, you'll see a 74 base pair insertion. So that can pose a problem for modeling because, well, the crossover that we have here gets modeled, with this bond, and we have, like, as I told you, these angle potentials that try to keep this at 90 degrees, and we have dihedral angle potential that will try to keep the two helices parallel to each other. So the sort of the model would try to make the DNA across that crossover look like this, which is definitely not what you want when you have 800 base pairs and nothing constraining the DNA to be parallel like this. In reality, what you want is to have the DNA stacked like this. When the tutorial that we have walks you through the process of finding and removing a particular crossover and then replacing it with a new kind of connection, in this case, an intricate connection, so that the two helices are basically just one piece of DNA, a double strand. Okay, so you can find our tutorial, first of all, on the workshop website under the tutorials tab, and then here under multi-resolution simulations of self-assembled DNA nanostructures. And then on the Amazon image, if you go to the desktop and open this TCVG tutorials, it's this one, which was modified today. And then the last place you can find it is on GitLab, which is where we're going to be updating it as we improve it. So if you guys want to give us feedback, we'll take those changes into consideration and try to make it better. So this is sort of the long-term location for the tutorial. So you can check that in 6 months. It may have been updated, and since it's tracks with Git, you'll have a full revision. And with that, I'd like to thank the center for hosting me for the last few years, and the NCSA for their help with developing the grounding dynamics engine that we use to run these simulations. And also my group, including Sartok, we're especially Sartok for work on this project. And then Overkite for Victoria Bertel, Sean Douglas for collaborators. So with that, I'll be happy to take any questions.
You said that the crossover input, you want to keep these two helices in parallel, anti-parallel condition, right? But if it is, as in a previous session, some cases you can make break here, right? One of staples can be like cutted.
Yeah.
So in that case, it's not. It will never keep it in a parallel condition, right? Is it included in a?
We do have alternatives, but the way we process the CAD nanostructures, every time you hit a crossover, it tries to keep things in parallel. So that's sort of
so to make better simulation result, it would be better to break not at crossover but at a helices. I mean, to make a agreement between the actual condition and the simulation. Because they can do simulation that doesn't include a case of breaking at the crossover. If you make break in a crossover part, keeping the other part connected, then this linker works as a flexible linker.
Yeah. So if there's just a single-stranded piece, it'll be flexible. Yes. Our model incorporates. I mean, it includes single-strand DNA. And really.
Okay, so it's just regarded as single-strand DNA.
Yes. Yeah. If you have only one strand, it's treated as single-strand DNA. Actually, you can see this in these slider objects. So these yellow regions are actually single-strand DNA, and this has been smoothed a lot, so you don't get a sense for how flexible they are. But you'll see when you run the simulation on your own. On the AWS, you'll see that. It's quite flexible, actually. And we used a similar strategy for getting potentials for the angle, the intrahelical or the intra-strand angles for the single-strand DNA. But there's a lot more variation. Like everybody pretty much agrees that the persistence like double-strand DNA is about 50 nanometers, maybe 45, somewhere in there though. But with single-strand DNA, there's quite a wide spread in the data because the measurements are not that correct. So we've picked, I think, around 15 angstroms, 1.5 nanometer.
Yes. Thank you. Very interesting. Can you also extend this explanation to, how do I say, to simulate some hybridization? The reason why we use OXDNA is that they can simulate or predict DNA duration hybridization.
So from the outset, my goal was to go from a CAD nano design to atomic structure. I didn't really want to try to duplicate what OxyDNA was doing. I don't want to compete with them. I think OxyDNA is actually quite a nice model. So my recommendation is to actually just use OxyDNA if hybridization and dehybridization is important for your structure, or if you suspect it will be. Now, what I would like to do is add OxyDNA as an output. So instead of running an all-atom simulation, you can run an OxyDNA. But I don't think it'll actually be very difficult. It'll be very easy, but I haven't done it yet. So it's just a matter of time.
Basically, what I want to ask, like modeling some box structure structure by your simulation and just simulate by OXDNA or something else to simulate this open close.
Yeah, I think there could be some interesting opportunities also to take something like this where hybridization is not allowed. Maybe run a structure for a while with a model like this and switch to OXDNA, run for a while, switch back. I don't know. I'm not sure if there's a way to do that, preserve a Boltzmann distribution, but you might be able to sample the space more efficiently than using either model alone. Right? Yeah.
And I have another practical question. 1 year before, I submitted some abstract to Nano can do service that is a bit huge and with some free loop at the outside, and it shows some, it replied some of error because of, I don't know, but perhaps it is too much flexibility or something. Is there any limitation or some barrier if you introduce a lot of single-strand DNA?
I don't think there's any inherent limitation. I mean, eventually, I'm sure you can break it, and I don't know what those limits are. So, I mean, I'd invite you to try it, and let me know if anything goes wrong. Actually, you can either email me or you can go to our GitLab page, but then you have to register. But if you go to our GitLab page, you can actually post an issue, onto our page for the mRDNA package. But yeah, you can also just if you have a problem, and if you can send me a structure, that'll always help a lot with tracking down the issue. Yeah, thank you.
If you you showed this kind of simulation in topological model, quite topological special structure, but sometimes initial condition is quite important for this kind of topological structure. How can you, for example, what if, for example, if you want to simulate the can this result, if you want to get the result in a catenated condition, is it possible to, if you make a certain appropriate connector or something with single-strand DNA, can you make it, or can we put the initial position to make it?
You can control initial positions. Yes. It's not trivial to do it, but it is covered in the tutorial, so it can actually be done. Yeah. It is possible, but it can be tedious depending on the size of the structure.
Okay.
Another question? Yeah.
I have a question for you and Gerald together. What are the limitations and advantages of your simulation versus Gerald's? Do you have any comments?
Let's see. So for us, we're using a less mature simulation package, I would say, compared between Deep Blue, which has been developed over the last decade or something. So there can be issues associated with it. The advantage, I think, which probably maybe not many people will use, I don't think it's actually possible to have potentials like this in Deep Blue. So if you have some niche application where you need to apply some force to your DNA origami object, or maybe simulate it in some nanofluidic trikes or something like this, maybe what we have is a good option, although working with these files is not trivial. And then as far as actually the modeling approach goes, I think we probably each have to test each other's tools out a little more.
Yeah, I'm just wondering, if I provide a common test system and if I compare with the a pointer finger structure, so which one will provide a better RMSD, so kind of
Sure. So, yeah, no, I haven't done this kind of comparison, so it's hard for me to comment. But we should do
maybe we should test it as users.
Yeah, do you want to add anything, bro? Yeah, we actually would like to have at least the that output of this, rigid body relaxation as input for this, because if you have, one of these structures that has very tangled sort of initial conditions, you won't get a good result from our method.
So, like, I would really go to a post-spin model, situation. Like when I was looking into speech body identification, just trying to support what was the problem. It's not very good showing in the design stuff. So, there is this, I can see that it's trying to, what I'm trying to do is I'm trying to see everything in place because this potential issue. So the idea is what I create right now will be obvious. And those are will be but this is so that speaking to the other program.
Yeah.
For the like goals that combine it's output that the other program.
Thank you.
All right. There are no more questions. So let's investigate the AWS image, right? So if you haven't transferred your files, is there anyone who has files there and would like to keep them? I mean, to save them? Yes.
There's problem with copying folder. I can copy the file, but the folder.
Okay, so there is a problem, right? Okay, we will have a solution to it at 1 p.m. But it's good for us to know that there is a problem. So there are some people who were not able to transfer things.
Yeah.
Like
files you can transfer, but not a full folder. I don't know. There's some permission problem. I don't know.
okay. Well, that's good to know. So maybe you'll talk to Chris and we'll figure it out. But for now, let's go downstairs. I think we're going to the first floor. The first floor. We're gonna have a picture near Mr. Beckman statue. Yeah.
Okay. So actually, my okay. That was pretty good. It's a good recovery. It's easy to do well in every.
Yes.
That was pretty good. Yeah, there was.
But I wanted to explain the model.
No, I think the hope, right, is that the people who don't care about the detail don't need to pay attention. People that care can.
Maybe not.
Well, that's the kind of thing that someone can look at those slides later on and try to work through the math.
Better part of I've been messing around with this.